Hello everybody, it's your friendly neighborhood root beer here. Thank you for joining me for more Apollonian problems, and as you can see by our GeoGebra setup, we're going to deal with the case where we have three given lines. We've got our pink lines here, and we want to construct circles tangent to each of these three lines. Okay, that's the goal. And with this problem, we have four different solutions. Now, you might be familiar with one of these solutions. As you can see, we sort of have a triangle. In general, any three lines will form a triangle. There are specific cases, like if two of them lie parallel to one to each other, and you'll get different solutions there. But in general, any three randomly chosen slopes, you're going to get a triangle. Okay, and with this triangle that we can see, you might think, well, gee, what sort of a circle touches the sides of a triangle? And that would be the incircle. Okay, and the incircle is exactly one of the constructions that we're going to make, but there's also going to be the X circles, which you may have heard of before. And they lie outside the circle, or sorry, outside the triangle, and are tangent to one of the outside, or one of the lines of one of the segments of the triangle, and also tangent to the other two sides of the triangle when they're extended. Okay. In general, when we deal with a triangle, it's just three line segments, but if you extend the lines, or the segments two lines, you get a situation like what we've got here. So we might ask ourselves, how do we create the incircle? How did we do that? And to find the incircle, which I believe I've covered in a video in the past, we use angle bisectors. So we're going to construct our angle bisectors. Now, it's not obvious what angle here we're trying to bisect. If we were just given a triangle, you'd say, well, obviously I want the one that heads into the triangle. But, of course, we can bisect other angles. And that's what the GeoGebra tool does. It for any lines crossing each other, it gives us both angle bisectors. It doesn't know which one we want, and in fact, we do want both. So we're going to do angle bisectors for each pair of lines. There we go. And you'll notice something. We have some nice little intersections. Okay? Three of them come to meet at a point here. Three of them come to meet at a point out here. Three of them, of course, meet at the incircle here. And three of them meet out here. Okay. So we get nice little arrangements like this that we can see, and each of these circles here, or sorry, each of these points here is going to be the center of our circles. Okay. And now the question is, well, where do I draw my circles to? Because I mean, if I just grab our circle tool here, how exactly do I get tangent? I mean, it looks like it's possible, but how do I actually figure out the tangent line? So that's the next step here, is where are these points actually tangent? So we're going to get rid of the well, not get rid of, but we're going to hide the angle bisectors for a moment. They've done their job. They've given us the centers of the three X circles and the one incircle. And now it's just a challenge of, well, where do I get my points of tangency? And let's just say, for sake of argument, imagine we had the point of tangency here for the incircle. What would it look like? Well, if it's a point of tangency, then we must have a perpendicular line when we connect up the center to that point of tangency. And that gives us the idea of what we need to do. What we're going to do is just pick a side, draw a perpendicular line so that it passes through these centers. And that gives us our point of tangency. And I'm doing it all with the same line. You don't have to. You certainly don't have to. But it helps me be a little more organized. Okay, and now we've got the points that we need. We've got a center, we've got a point that we know will have to be on the circle. We can draw our circles. Just hide these lines, and now let's grab the circle tool, but as we've got the solutions now, we're going to mark them in red. There we go. There's the in circle. There's an X circle. Another X circle. And the final X circle. And there's our 4 solutions to the general case. Now we'll just hide all our work because we're fancy like that. No need to keep the in center around. And there we go. 3 arbitrary lines, 3 general lines in an arrangement, and we get 4 circles here. And we can even scale things around. So there's our 4 general solutions. Now, I mentioned at the start, you can get failures. I'm trying to mention the failures, the exceptional cases, a little less and less. But let's just talk very briefly about the failures. Okay. There we go. So suppose we had our 3 lines, and they were all parallel. Okay. So just like I mentioned it briefly when we did point-point line, you couldn't have the line separating the 2 points because you wouldn't get a circle that will be tangent to the middle line. And that's the exact same reasoning here. Imagine we had a circle that was tangent to each of these. We'd get 2 tangent points. Maybe these are tangent points for our hypothetical circle. If indeed this were the case, we'd get these 2 tangent points, and then, well, they're separated by this middle line. So for the exact same reason that you can't get a solution to the line point-point case when the line divides the 2 points, the exact same reasoning applies for if you have our 2 lines separated by another line. But that will only happen when all 3 are parallel. Okay, so all 3 parallel, none of them parallel to either of them. There's one other case, and that's if 2 of them are parallel. So we'll draw that in, and then our third is not parallel. Okay, if it were parallel, I just explained that's not going to cut it. That won't work. You won't get a solution. Now, let's just suppose we had another line. Okay, and we'll make them all pink. And suppose we had this very special, very unique starting case. You wouldn't expect to get a whole all 4 solutions like we had in the general case because we've limited things. We have extra knowledge. We have one line that's parallel to another. And indeed, in this situation, you won't get 4 different solutions, but you can get 2 solutions. Circles in here, circles in here. But you're not going to get a circle out here because one of the parallel lines is blocking access to the other line, in a sense. The lines have to be tangent, so the circle can't go through this top line to become tangent to the bottom line without, not being tangent to the top line. So we get problems like that. Okay, so how do we avoid this? How do we get around this? Well, when we used our angle bisectors, we got intersections, but we only needed 2 of them to determine the center point of our triangle, of our circle. We do the exact same sort of thing, get these intersection points, and then, well, what did we do before? We used the perpendicular line tool. Okay, so we'll get out our trusty perpendicular line tool. And we get some intersections here. And this allows us to create our circles. But there's only going to be 2 circles instead of the general 4. Okay? And that covers all arrangements of lines, but the one I really wanted to focus on was the general solution. 3 lines with 4 circles, and the 3 lines are not related in any way in terms of their slopes. Okay, but there's a special case for those of you who like that sort of thing. Okay, notice that these 2 circles will have to be congruent circles because they both touch the they're both tangent to the parallel lines, and so drawing those perpendicular lines from the center to the point of tangency, we get that the diameters here are going to have to be the distance between the parallel lines. And that's just a nice little fun observation. So join me for more Apollonian problems in the next video, and I will see you guys there. Thank you so much for watching.